See here, when I export the model, I can export it based on checkpoints. I have a checkpoint every 100,000 steps. So we can see, like, if I use, and it's like kind of easy to plug in. Like, you just have what's something called behavior parameter, and you can plug any model. So the one that you saw at the beginning of the video was the most performant model, or the most performant agent. That was a checkpoint at 900,000 steps. But if I put the one at 200,000 steps here, and if I run the agent, you will see that it's still learning. let's say it's still learning, but it's far from perfect. It can still beat, but it will just crash into the first wall it actually encounter in front of it. If we go to the checkpoint at 400,000 here, and we do the same, we can see that it kind of progressed. Now it is able to steer a bit, but when it faces a kind of more tight angle, it will crash to the next wall. And it is how it learned. Actually, this agent was able to complete a full lap around 600,000 steps. It was able to complete like the lap successfully, but it was kind of slow. As you can see, it is still kind of slow and very hesitant on what to do. Instead of what we can see when I let it really run for like almost 1,000,000 steps. Now it is able like to move at a faster pace, have a very clear decision on how to make it and how to run. So as you can see, it is really like even like kind of drifting, and I really like that a lot for this one. And as you can see, it is really good. In this video, I'm going to show you exactly how it works, or how the environment is set up, how the algorithm is done, how the training data is passed. And at the moment, it finally learned to complete a lap, as you can see it in here. Let's start with the problem we are trying to solve. We have a simple oval racetrack in Unity, a rectangular loop with an outer wall, like here, or outer boundary that is considered a wall, and an inner island, also, which is a wall. That is how we created this track. The car starts at a fixed position here and needs to drive around. It is very simple. The naive approach would be to just write the code. If you are far to left, steer right. If you are far to right, steer to the left. But that is kind of brittle and handcrafted. And it doesn't generalize actually, because when this track evolved and become more complex and everything, like, it won't work. So what we did is to have an AI discover a driving policy. How does it drive to go around the corner, to avoid the walls, etc., etc. And to do that, we need to define 3 different things. And this is the core of any reinforcement learning problem. The first one is, what can the agent observe? What information does it have to take into account at each moment? The information number 2 is, what action can it take? Can it go around? Can it loop? Can it move forward? Can it move backward? Etc., etc. And the third one is, what is trying to maximize? What count as doing well? Is it going through the wall is doing well? Is it going backward doing well? Is it passing through this green area doing well? Etc., etc. And let's go through each one. So for the observation, the agent doesn't see visually actually the track. It gets a flat vector of 53 numbers every frame. Here is the important design decision. The agent has no idea where it is in the world. There is no GPS, no global map, no X and Y coordinate. Everything it receives is described as relative to itself. It only perceives those stuff that are around it actually. The biggest chunk of the vector map, which is out of the 53 values, the 30 come from a look ahead over the next 10 points on its track. For each waypoint, the agent get 3 numbers: how far away it is, what horizontal angle it is relative to the car, and what vertical angle. Because I want to have in the future a track that can have elevation and steep, those type of stuff. The agent can't ask where am I in the track. It can only ask what is near me right now. Think of it like you are driving in a thick fog. You can only see the next few road markers ahead of you. That is exactly what the agent perceive right now. The vector also includes the car velocity based on its own local frame again. The forward speed, the sideways drift, vertical, and single number for how far it is sitting off the center line. The center line will be like the middle of the track. We can call it like that. So for now, the remaining 35 slots are all zeros in the phase 0 that we are right now. They are reserved for curvature, lap time, the resource state, the opponent position, because it is a racing car. It should have some other opponent that race and try to see which one get to the end of the track first. The architecture is already designed for phase 1, and I will show you later how it will work. So the action are pretty simple, I would say. The action output exactly 2 numbers at each frame for now. The first control the drive. Positive means throttle, negative mean that you are going backward. The second one is steering. -1 full left and +1 full right. And it can take any position between those two. This goes directly into the Unity engine via additive forces. There is no built-in car controller, just a rigid body. Now, there is one important thing that we need to take into account when we do reinforcement learning, which is the reward function. What is the reward function? The reward function has 3 layers. The first, fire every single physics frame. The agent actually earn a small reward proportional to how fast it is moving forward. The forward is important. I don't want the car to move backwards actually. Go fast in the right direction, you earn a little. Slow down and or drift sideways, you earn less. Go backward, you get penalized. This is the constant pressure that teaches the agent to keep moving forward. Second layer is a checkpoint system. There are 8 gates around the lap. Hit one in the correct order, you earn like plus 0.2 reward. You hit one out of order, say the agent tried to cut back through a gate, it already passed and it lose 0.2. Complete all gate in sequence and earn a bonus of 1 plus 1. And the episode ends successfully. That makes a clean lap worth 2.6 from checkpoint alone. If you account the fact that whenever it moves forward at a certain speed, it gets also a reward. These two combined will get you like a lot. Now, the third policy that I put in place is the touch wall. If you touch any wall, the inner wall or the outer wall, you get a penalty of 5 points, and the episodes end immediately in failure. That is 25 times the value of a single checkpoint. This message is hard to misread. Walls are catastrophic, so the agent need to stay on track. So you combine all of these to have a perfect lap that you pass all the checkpoints in the right order, you move at the correct speed, you don't touch a wall, you will get a total reward of 5.6. So the bot is designed to maximize its reward. Now, but if with all of that, how the agent learn actually? And it is I want to say it's simple. Like, it's kind of simple. It is there's something called proximal policy optimization, and the short term is PPO, which is one of the most widely used reinforcement learning algorithm actually today. We implement it from scratch because I want to take control of what it does, because a way to make it better in the future is to kind of change a bit how the PPO works. The agent has a policy. The policy is actually just a neural network that take all the 55 or the 53 observation value as an input and output the true drive and steer value. At the start, and people who knows like machine learning, traditional machine learning, and like a deep neural network know, like at the beginning, all of these 53 observations are kind of randomized. Have random weights. The car output random action and it will probably crash immediately because it doesn't know where it is. All these values are just random. We let the car run for 2048 steps. We collect the actions, the reward, and the observation. This is called a rollout. Then we use the data to update the network weights. Actually, the network weights is just what are the parameters. When you hear that people saying the new version of ChatGPT have 5 billion parameter or 10 billion parameter of like 100 trillion parameters, those are actually the weights of the models. So we take the rollout. When we have the rollout, we use those data to update the neural network's weights to make good action more likely to be performed and bad action less likely to be performed. Then we collect another rollout and we repeat. The key challenge is that aggressive update can destroy the policy. For example, one policy is to move forward. Because this is experimentation, the next rollout can produce a policy that tell it goes backward. And this is like a very drastic change in the weight. So what we do is we don't want the weight to change too much from one rollout to another rollout. And the car forget everything it learns. So what we want to do is the PPO to solve it. It is called the clipping mechanism. It limits how much the policy uh, can diverge from one old one in a single update. This make like training stable. Look at it almost as the learning rate that you have when you do a deep neural network. When your learning rate is too much, you can overshoot and your neural network is going to diverge, if you call it if you can call it like that. We also have something called a generalized advantage estimation to figure out which action were actually responsible for the good outcome. Because we are collecting a reward for 200 steps, um, it can feel like the first action can be a very good action. So we need to make sure that the earlier actions get credited back for the positive outcome. The discount factor called gamma control how far into the future the agent cares. And we can see that later. We did the training for about 1 million step. 1 million step is like, is not that big for a reinforcement learning algorithm. This is the reward that you can see here. And we approximately, I stop it actually at 927,000, something like that steps. The x-axis in the training timeline in millions. Each faint blue dot is a single episode. The cyan line that you can see is a rolling average over the last 10 episodes. The orange line is the smooth line so that people can understand what they are seeing. So look at the first 600,000 steps. It's kind of flat, negative, and noisy. So the car is crashing actually a lot. And actually it is crashing almost every episode. but something is happening under the surface. The policy is slowly learning which action are less bad, building up a very rough understanding on how to not immediately crash. Then look at around uh, 0.8 million steps. We see that this is a breakthrough. This is the first time that the car, our car, is able to do a full lap without crashing. And it did it, and the final reward was around 4.5 because it was very careful. It did not speed that much, and it take like a lot of time to complete it. So, but still, it was able to completely do a full lap. And this shape, this type of shape in this graph is like typical of a reinforcement learning problem. Long plateaus and sudden jump. The exploration phase is doing invisible work the whole time until eventually all the pieces kind of connect together and the agent find a complete solution. What we are seeing right now is what we like the entropy curve. The entropy measures how random policy output are. And we don't want actually the policy output to be like to be random. High entropy exploring widely, so which mean like when the entropy is high, we are in an exploratory phase. When the entropy is low, we are converging to a specific action it prefers. For example, when there is no curve near the car, it should not steer, it should just go forward. These are type of stuff that it will learn. And we start at around 2.86 and we end at 1.24. The agent is steadily becoming more confident and less random at training progresses. The fact that it never collapsed to zero is healthy. Some explorations keep the policy robust, which means even if our track is pretty linear and straightforward, the agent did not really memorize the road, if you can call it like that, saying it have to move forward for X amount of time, then turn left for X amount of time, then turn left, etc., etc. So it still have a certain bit of exploration. So when you run the same agent with this model in Unity, it won't always replicate the same route. It will try some different stuff. It will steer at different angles, etc., etc. And if we combine both, you can see that when the rewards climb, the entropy falls. The agent is learning a specific repeatable strategy rather than acting randomly. Once the training is finished, and for me, which is also a very interesting part, it is the ability to wire this agent directly into Unity. And we did that using something called ONNX. I think people call it ONNX. So the phase zero, this is really a phase zero that I wanted. It's just a proof of concept. We can learn that this problem is solvable, kind of solvable, at least using reinforcement learning. The car learned to drive in a consistent kind of rectangular oval from nothing in under a million steps, which again, a million steps is not that much for this type of problem. Phase one is where it is getting interesting, and we will introduce a more complex track with like different layout, a variable starting position, so that the agent can't just memorize one trajectory, and eventually all the agent on track. Those are the opponents that it's trying to sometimes avoid. We can have like static opponent. It should be able to avoid them and those type of stuff if you want to overtake. The 35 reserve slot in the observation vector are already waiting for those features. Like there is the curvature, like is the road. For now, we only have like very linear road, but we can have curve in the road. I will also be going to time how much it does to do one lap. the opponent position, and the architecture carry forward unchanged. So the architecture won't change for now. The policy might change, the reward function might change, and those type of stuff, but this is the idea. If you want to follow along, and as we build this out, please subscribe, hit a like button. The full phase 0 code, I will put it in the link so that you guys can try it and give me your feedback if it works for you.